by nature, explorers. The same curiosity that sends us to the stars at the speed of thought urges us to go there in reality. And whenever we make a great new leap, we elevate humanity, bring people and nations together, usher in new discoveries and new technologies. So remember to look up at the stars and not down at your feet.
Hello and welcome to Sunday. Sunday, a day of rest. Probably not anymore these days, everybody has to work. So Sunday actually comes from the older German and Norse mythology again, which seemingly most of them do. Either German, Norse, Roman or Greek. So it's old language and it's usually showing the sun as a goddess named Sunna or Sol, which we know our sun's now called Sol, not Sunna, not so much. Now our ancestors probably saw it as a goddess due to the life it gives our planet, the warmth and the sun creating life and plants and all that stuff. So like in the animal world, where generally the female of the species are the life bearers and the creators. Therefore, it's a woman called Sunna or Sol, or a representation of one. So Sol was born out of a dense nebula that collapsed in on itself around about 4.6 billion years ago. That's the sun, by the way, not the goddess. And it is an average sized sun with nothing particularly special about it compared to the other stars that are out there, but it is still pretty massive. So it's 99.8% of all the mass in our solar system. So it's around 750 times the mass of the entire solar system. So all the planets, the asteroids, the dwarf planets, me, you, we're all just the leftovers from the sun. It's just 0.2%, so not even 2%, so we're absolutely tiny really. Now it's a huge ball of plasma. It's pretty much a power station in space eating hydrogen to create helium through nuclear fusion. When this happens, it throws out tremendous energy, heat and light. Now this light takes only about 8 minutes to travel from the outside of the sun across space and to Earth for us to see and feel it here. But it travels 93 million miles in that time, on average, depending on Earth's position in orbit, of course. Although the charged particles inside the core, which is around about 15.7 million Celsius, pretty hot, can actually take over 100,000 years to actually get to the sun's outer surface and then blown towards us, creating the solar wind, which causes the aurora that we see on Earth. Now the sun rotates on its axis once every 27 days. However, its equator spins faster, taking about 24 days to rotate, while the poles take more, kind of around about 30 days. So as you can tell, the sun has different periods of rotation because it's all gas and plasma and all sorts of things going on there. Now the layers of the sun, you've got the corona, which is the outermost part of the sun's atmosphere, and it's a bit weird because it's kind of hotter than the inside. So say you're sat at this is something I read by NASA, which I quite liked. You're sat by a campfire, you can feel the warmth, you get up and you walk away, maybe to pop to the toilet in a bush or something. As you walk away from the campfire, you actually get hotter than if you're closer to it. That's what it would be like being by the sun. So the corona is a little bit strange. You've got the chromosphere as well. It's so hot there that particles can get enough energy to then escape the sun's gravity as solar wind going through into the corona, heating up and then carrying on into space. You've got the photosphere, which is the visible surface we can see using special filters on telescopes. You've got the convection zone. Now here hot gases kind of bubble to the surface, rising and falling back, making the sun look like it's kind of boiling on the surface. It all looks boiling that if you've got the right telescope. Hydrogen alpha is quite a good one to do that. Then you've got the radiative zone, and this is where the energy is radiated from the core, slowly moving up through the sun. So it radiates the energy through and up. Now, what can you see on the sun? There's lots of sort of phenomena you can see. One of them sunspots, and they're pretty much just spots on the sun. They're dark, cooler areas on the sun's surface. They're around about 930 to 31,000 miles across. So that's quite big. They can actually be bigger than planets. So I always say it's kind of like a sunspot's kind of like cooking porridge. Cook it in the microwave, it heats up on the bottom, goes up to the surface and spreads out all over the microwave. So that's what they do, they come up to the surface. The reason you can see them is because although they look dark, if you put one in the sky, it would actually be 10 times brighter than the full moon. So although they look black to the surface of the sun, it's because they're actually cooler than the outside of the sun, as we spoke about earlier. So you can see them as black spots, but they're really bright and still really hot. Now the dark spot on the actual sunspot is called the umbra, and the lighter area is called the penumbra. And their amount depends on the sun's solar cycle. It's about 11 years. You have a solar maximum, solar minimum, and like during the solar minimum you can have sort of like none at all, which we've been having recently. There's absolutely no sunspots in the sun at all, and you can have up to 100 being reported during its maximum. Apparently I've never seen that. I've seen 3, 4, 5, 6 maybe. Now the first rule of solar astronomy, or looking at the sun, is don't. Never look at the sun. It's bad for your eyes. If you look through it with a telescope or binoculars, you'll go blind. It'll be the last thing you ever see. So don't do it unless you're with a professional like myself and I can show you what to do. So to see them, you'll need to get a certified special filter on your telescope, and make sure you know how to use it properly and safely. And if you are getting your own, talk to the people in the shop, actually ring them up and have a chat with them, make sure you've got the right one for your telescope, because these filters take all the heat and the light out of the sun, making it safe to view these cool objects that you can see on the sun. So if in doubt, don't do it. You can always come to one of our events or events around the UK that you can find on the Go Stargazing website. There's a map on our website as well, www.ukastronomy.org, and find a local society or event your way and ask them. That's the best thing to do. So if you have got the gear, you know what you're doing, or you're a professional, what can you see apart from sunspots? Well, there's a solar prominence. Now prominence is a huge bright loop or cloud of plasma, thousands of miles long, extending from the photosphere up into the corona layer of the sun. Now these can last from up to a day to weeks to even months. They often loop from sort of one sunspot up and over to another sunspot. So I always say it's kind of like a battery. It kind of goes from the plus to the minus, and often they can get all twisted up like an elastic band, and when they do, they then snap, and this throws the plasma out into space. You will need a particular filter or scope to see this wavelength of light, and it's called a hydrogen alpha. There's a telescope called a Coronado, which is a specialised telescope for looking at just this. They are quite expensive. I think they range from about 400 to 8 to thousands of pounds. We're lucky we have got one. We got one donated to us for half price. So we get to see this and actually show you bits of plasma being pulled out of the edges of the sun. So when they get all twisted up and they snap, you get a coronal mass ejection, or a flare as I like to say. Now this is when a huge clump of plasma breaks away from the prominence and it's thrown out into space at a speed of between 155 miles per second to 1,865 miles per second. The fastest they can reach our planet is in about 15 to 18 hours, I believe. So that's how people can say, oh, there might be some flares coming this way, you might get to see some aurora, because when it interacts with our atmosphere and our magnetic field, it creates the northern and southern aurora, which are really, really cool to see. So that's when we know there's a strong aurora on Earth, and we might be able to see it from the north of England, maybe even further down, depending on how big it is. Now, don't be too scared about this, because the worst case really that's going to happen if one does hit and it's really big and it does kind of get into us on Earth and mess around with things, it's just going to knock out electrical objects. So yeah, power stations might go down. I think one happened in the 80s or something where it knocked out a certain area. So really, cars, PlayStations, Xboxes, all those things, phones, are all going to get knocked out. So no Fortnite for the kids, no Call of Duty for the adults, and we're just going to have to talk to each other really like the good old days, sit down, have a chat. Now that could seem quite terrifying for some. Now there's a few other things you can see. You've got a solar filament, which is pretty much a solar prominence, but viewed with the sun as sort of the backdrop, so it's not on the edge of the sun, so it's across the actual sun itself. And this looks like a dark wisp across the surface. You've got faculae, which are bright, intense, active regions associated with the sunspots. So they're sort of like where the sunspots are, there's bright, intense areas around the sort of edges of them, and that's what they are. and then you've got spicules, which are short-lived jets of gas. The granulation you can see on the sun is generally the appearance of sort of the photosphere, which we were talking about, bubbling away and looking as if it's sort of boiling up as all the gases move around and come to the surface of things. You also have a really cool thing known as a solar quake. Now, often after a flare, a solar quake will follow, and it looks like the ripples in a pond after a stone has been thrown in. As you can see from the video, they're quite cool. They are massive. They're about 2 miles high, these ripples, and they move at 250,000 miles an hour. And they will have travelled 10 Earth diameters within an hour. So within an hour, they would have travelled the length of 10 Earths. Now that's not far off of Jupiter, is it? Remember we said if you've seen the Jupiter one, how many Earths can fit inside Jupiter? I believe it's 11, something like that. Go back and check it, because I might be wrong. So that's pretty impressive. Now, what's going to happen to our sun in the end? So in around 5 billion years, we've got a bit of time yet, the sun's going to swell into a red giant. It's going to consume all the inner planets as it expands, including us and up to Mars, they think. So all the way up to Mars, it's going to expand out and get bigger and bigger and bigger. It will then begin to collapse again on itself, turning into a white dwarf star. But before it does that, it will eject all of its outer atmosphere, almost like its kind of last breath, as it's kind of going, oh, I'm done. Throws it all out back into the solar system and out into space and the universe. And this creates a planetary nebula. Now, it was called that, but I don't actually think it is. It doesn't create, well, it does create planets in a way, because all the stuff that gets thrown out, all the elements and that, will then merge all together in other gases and create more planets and stars, hopefully. So in a way, planetary nebula, yeah, makes sense. And you can see these sort of things if you look at, say, the Ring Nebula, which you can see down the bottom there on the picture. And also you've got the dumbbell above. Now that's just looking in different ways. One's looking straight on, one's looking to the side of these two nebulas. And right in the middle of that will be the star, the white dwarf, where it's died and thrown all this gas out. So it's something really cool you can see in the sky. You can see the death of these stars and all the gases and heavy elements and stuff getting thrown out. Not as heavy as supernovas. When they go, they have to be big stars, but we'll talk about them in another talk. When they explode, they really do explode. This is just a load of gas just being thrown out from our star, and our star will still be there. I believe it will go from like a white dwarf to a brown dwarf to a black dwarf. We won't be able to see it anymore. That's our nearest star, Sol, and the origin of the day Sunday. So please do remember to never look at the sun. It's not good for your eyes, and it's not good for me either if you do. So clear skies, and remember, there's a billion worlds in your back garden.